Okay, so as I promised, I'm going to, you can hear me, right? You shouldn't be sitting that far and making me talk loudly. Practice. No, anyway. Oh, what I was saying, yeah, so as I said, I'll be talking about something called random orders, computing random orders in high dimensions. Obviously, explains what random orders are, and why they're important, even in, it's actually very important in database query systems. We knew. Okay, and this work is actually a very old work of mine when I was doing my master's thesis. I don't remember a lot of the details actually. Because it uses a lot of probability theory and I've forgotten some of the stuff. But we'll figure it out. Okay, let's look at the slide. Let's define some things, extremely abstract way, then we'll move to a visual description and definition. Okay, so I'm first defining this operation, successor. So if P dominates Q, that's how you should read it. P dominates Q. For 2 points P, Q in a Euclidean space of k dimensions. Everybody knows what a Euclidean space is.
I forgot what it is.
Like a vector space?
Well, vector space has a different meaning. Well, so it's
It just has a
so in plane, right? A plane is a Euclidean space of 2 dimensions.
Okay.
And this k could be arbitrary.
Because you just have to have 3 different things, like the triangle inequality applies, shortest distance is a line between 2 points, maybe,
Yes,
something else.
it's a matrix space, and but plane is that example in 2 dimensions. We say P dominates Q, or P is above Q if for each of the components of P and Q can be thought of as vectors. So for each of the components of P dominates individually greater than equal to the components of Q.
So that means that that's only a weak ordering?
So for example, it's a partial ordering.
Partial ordering.
So for example, for a line, it's just a case of total ordering. As long as the value of P is greater than Q, if it's one dimensional, just a line, it's only one value, then P dominates Q. This is the set of points we are given. We are given n points in this space. I don't know. It's weird. We define the first maximal layer. I promise the next slide has photo of it. This is the first maximal layer, that's why I'm saying M1, of this set of points of P as the set of points that are not dominated by any other points. So if it's just a one-dimensional line, there can be only one point, and that will be the maximum of that set of points. But for 2 dimension, you can have more than 1 point. We'll see in the next slide.
Would they be points or they would be spaces?
No, this P.
No, I mean in the first. I'm sorry, a bit behind, but.
We'll look at a forthcoming
Okay.
diagram. It will make clear. And the eighth, a handful, mouthful, maximal layer is defined recursively. So to define the 8th maximal layer, you remove the first to h minus 1, you left with the subset of points, and the first maximal layer on that subset of point is the 8th maximal layer of the entire set. So think of this as a generalization of ranks of a totally ordered element in one dimension. So you have rank 1 element, so that's the max. If you remove the max of the rest is the rank 2 elements. So here in high dimension that corresponds to layers. Instead of, because you're not going to have just one element, you can have more than one element. Or no element. Okay, so let's look at this example first. Then we'll go over this. So I have here 8 points in plane. And these chains, right, represent different maximal layers. So as you can see, these 2 points itself are not dominating each other. because in one of the coordinates, x2, this is higher, but in x1, this point is higher. So by the definition, none of these points dominate each other. So they belong to a maximal layer. And it turns out none of the other points dominates them too. So they belong to the first maximal layer. Now if I remove these 2 points and compute the maximal layer of this set of 6 points, I get this. So this will be our second maximal layers. Now note that each of these 3 points is dominated by at least 1 point in the first maximal layer. So if a point is inside this region, it will be dominated.
Excuse me, I still don't understand how can be more than 1 point. I mean, how can be more than 1 point in the maximal layer M1? So it says it should dominate all other points in the set.
No, so the layers form because they are mutually incomparable.
No, in the first layer,
Yes, so as I said here, right?
Yes.
Why are these 2 points here?
Yes.
Because none of them dominate each other, so they're incomparable. So they both belong to the same layer. In this case, the first layer.
But
You don't dominate the others two.
So the leftmost,
This one?
yes,
Mhm.
that one makes sense because it's the highest point.
So,
So in
so
the
we
Y,
don't have a preference on the dimensions.
Yeah.
Directions, right? So in x2, this direction, this point is greater than this point.
Mhm.
But in this horizontal direction, this point is greater than this point.
My question would be though, why isn't the rightmost point in the second layer in this first group? Because it has the highest in the x1 direction. So wouldn't this maximal group, shouldn't it be the?
Oh, good point. Yeah, this actually is incorrect. There should be
Yeah.
this one, 3 points.
Okay.
Yeah, any point which is maximum in one of the direction clearly cannot have any other points dominating.
So, but to finish that off, shouldn't each of these layers have a maximum of 2 points in them?
No.
Because there should be,
Yeah, that seems confusing to me.
So for example,
Could you define the maximal layer one more time?
I'll give you an example where all the points in one maximal layer. So in this case, if they form like a cycle, right? None of them dominates the other points. They're all in the same maximal layer.
how can you say that none of them dominate? Because shouldn't the rightmost and the leftmost dominate?
Well, in one dimension, in order to dominate another point, you have to dominate in every dimension.
But there's only 2 dimensions here.
Yeah, but if, see, this point, right,
Mhm.
dominates this point in this dimension. But in this dimension, this points dominate this dimension.
If there's
So
a
they're
point on-
incomparable.
If there's a point on the very rightmost and very top, that dominates everything else, right? Top
No,
left,
if
top
the-
right
if-
would
if-
dominate
if-
everything.
If there is a point here, right, and if I draw this thing,
That
all
dominates
the points inside this will be dominated by
Yeah.
this one.
Ah.
Because these things will never intersect.
So then in
But
this
we
situation,
don't have such a thing in the,
So, what? How did it move here?
you click it,
Uh,
can you go one back? Yes.
So as you see here, right, something dominates it for every dimension, its value is at least that or greater.
so then in this example, the first maximal layer with that point in the upper right would be the upper right one, and then those 2 down right there?
All of them will be in the same layer.
So if we have that circle,
No,
What is your
like,
question?
I think what Ava is showing here is that you can visually think about dominating in this 2D plane
Right.
as being everything that would be inside of the boxes that we're drawing.
Right, okay.
But if you notice, none of the points that are on that line,
Are inside the box of another point.
yes.
Okay.
So
They're
if
all
you,
incomparable.
yeah,
Okay, so if I understood things very well, so let's say we have 2 points, A of which has coordinate 1 and 1, and then B which has coordinate 2 and 2. So B will dominate A because the x of B is higher than.
I got lost. We'll talk.
Yeah.
I need to kind of move a bit. There's a lot of stuff.
But it
going on.
dominates on both axes.
In both axes, exactly in both axes, and x and
And
y.
before I proceed further, most of this work is in high dimensions. So after 3, you kind of lose track. In 3, instead of this square, you have this kind of a cube thing going on. And beyond that, you lose track of it. So I should point that out.
Actually, I guess.
And so now everybody's clear on what maximal layers are, right? Before we move on. This is very important.
So my question was, if there was a point at that circle on the top right,
Where?
top right,
Here?
yeah, right there.
Yes, and then all these points will
So it-
be dominated by this point.
But
And
then-
so this, and this will be the
like,
maximum.
would that be that layer?
Sorry for this diagram was, in this case, yeah.
So
This
in
should
that-
have been in the first maximum.
So in that case, the second maximal layer is those 3,
The second maximal layer would be these 2 points.
but would it also be the one?
What is different? Okay.
The problem here is, it's kind of not clear. This thing is in like this is.
Wouldn't it be the one on the bottom too?
So
Yeah,
what
but
is
there
different
is-
maximum layer?
The bottom one?
This one?
No, left. There we go.
This
would-
one is, so this one is, yes.
It would
The
be on
problem
second.
is, once we move this up here,
Yeah.
it's not so easy.
It changes.
Correct, yeah, it changes. Anyway, this was a bad example. I don't know how it came right. This should have been in the first maximal one.
We don't have any maximal layers here because each point.
You always have a maximal layer.
No, because maybe I'm wrong, but you said.
Okay, let's go
If
back.
you set up points
We
that are
haven't
not.
gotten past what a maximal layer is. If I give you a bunch of points, right? Right, let's start from the, if I give you a bunch of points, and this is a definition of dominance. So a point P dominates another point Q if in every dimension the components of P is greater than equal to the
Yeah,
components
and
of
in
Q.
that picture, there is no
Now-
point that is dominate, that
Hold on,
dominates
hold on,
everything
hold on.
else.
Now, if for some point P, there isn't any other points that dominates that point P, then it belongs to the first maximal layer. So in every set of points, you must have somebody in the first maximal layer. So think about just a set of elements, one set of integers. There's always going to be a maximum value, right? Similarly, it's just an extension of that. So you'll always have the first layer. There's no guarantee you're going to have the second or third layer, but you must have the first layer.
So,
Well,
so everything there is in the first maximal layer.
No.
Because everything dominates something in some dimension.
No, no, no,
It's the
if-
question of if it's not dominated by something else, not if it dominates
So
something else.
it's not dominated because it dominates in some dimension, so it's not dominated by anything else.
So you could be dominated and you couldn't dominate something else too simultaneously.
Right.
And so that means you'll be somewhere in the middle.
Right. But
If now nobody dominates you, then you are in the first layer.
so
And
no-
once you remove it, in the rest of the subset of points, you find this first layer, which would be the second layer in the overall scheme of things, and so on. Okay, so what is a random order? That's the central point here. P is a random order. Oh, so why this problem is important? Well, in database system, this is also known as Skyline queries. So in a database, you have this set of calls attributes, right? For each kind of data entry, you have a set of attributes. And you can plot the data in some space where is by the number of attributes and their cardinality. And then you can argue which of the set of data points is in the first layer. So for example, if anybody knows multi-objective optimization, Right, so you have Pareto fronts, right? You have a set of optimal values because there are many objectives, they're incomparable. So in one objective, one value might be better, but in the other may not be. So that's another example here. So this does come about in actual situations. And of course, in an abstract sense, this is a generalization of sorting to higher dimensions. Okay, so P is a random order if P is built by picking points uniformly at random from the unit K cube. So you can think of each dimension spans from 0 to 1. And by the way you choose a point is for each of its component, you pick a value between 0 and 1 uniformly and independently from the other dimensions. So if I have a plane, right, I'm going to pick a random point by taking the x coordinates of that random point uniformly from the interval 0 and 1, and then independently picking the y coordinate of the point from the interval 0 and 1. And that generalizes to higher dimensions. This is exactly equivalent if P is picked uniformly at random from, it's messy. I'm not going to explain. If you understand this, it's fine. It's basically the Sn is the symmetric group, so it's the set of all permutation of n elements. And Snk is the Cartesian product of xk symmetric group Sn. And if you pick one point, if you pick, so a point in element of Snk is basically a random order in k dimensional points. But anyway, forget about that. And they can be shown to be equivalent. We don't care. The expected height. So what is expected height? So, oh, I forgot to define this. So the height is the number of layers, kind of obvious. And the width is the size of the largest layer. So in this case, this is incorrectly put in here. This should have been with the first layer. So the width would still be 3. And the height is also going to be 3. So basically this question asks, suppose if I pick these points randomly as I defined here, what would be the expected height? So it was known like 30 years ago, I think this was for 1988, yeah, around 30 years ago, that the height of H, the expected height is the kth root of n. So if you have n points and the number of in k dimensional Euclidean space, and they're picked randomly, then the expected number of maximal layers is the kth root of n. And the width is 1 minus 1 over k, n to the power.
Excuse me, what is K, what is N?
The number of k is the number of dimensions. So here I was giving an example in 2 dimensions.
Yeah.
K is generalization of any numbers.
And N is the number of...
Yes, so okay, and the size of the first layer, we discussed this, right? The first layer cannot be empty. And the expected size of the first layer is a polylogarithmic term, log n to the power of k minus 1. So you see that the first layer is quite substantial if the number of dimension k is quite large. So if k is 1, right? It's just a one-dimensional line, there should be just 1 point. That's the maximum. But k is 2, this equation says that approximately log n points are going to be your first Pareto front of the first layer. So it's quite substantially grows as the number of dimensions grow. In fact, what happens is this set of layers creates like an onion shape. So the first few layers are very fat and then this quickly kind of decreases. Okay. So here I have highlighted these two because this is no longer true since I have made the slides. So recently somebody did came up with asymptotic formula for the kth layer. And I'm not going to go over its complicated formula. And this is also not true because since it's not ongoing anymore. But we showed that this expected size depends on the expected longest increasing subsequence of so if you pick if you have n elements, right, and you have a random ordering of the n elements, right, what is the expected size of the longest increasing subsequence? That's an important question, right? So because it's not it's a random ordering, so you can have this kind of things. So you want to figure out the longest trend, in a sense. So there is no closed form formula for that. Okay. So for a random order, because you pick the points in a continuous interval, the probability that for some component, some dimension, they will share a coordinate is 0. It follows from the fact that
Same, with the same points.
well, yeah. So because this is discrete and you're picking, so if you it's a
Wait, for the discrete case?
what?
For the discrete case, it's 0?
Oh, so basically, because the real line is continuous, the
Right.
probability of if you pick something is equal to a discrete value is always going to be 0.
Right, yeah. Oh, okay. Yeah.
Okay. These are some of the previous results. So as you can see, the problem is we want to compute this set of maximal layers. The one we described, right? So you're given a set of points, we want to compute all these maximal layers. And as you can see, this result has a k here, right? So it can grow quite quickly if k is large. We want to avoid this, because think of it this way. If I compare all points with each other, right? Can we, in order n squared, number of comparison, compute all the layers? If I compare all the points with each other.
Can you ask that again?
So here, right, this is a deterministic algorithm of computing all the maximal layers. And it takes n log n to the power of k minus 2. Because this is an exponent, right, as the number of dimension grows, these things could grow. Like if k is log n, this is already like super polynomial. You're certainly not going to use this algorithm, right?
Okay.
So you can just at that point compare each point with every other point,
Yeah.
right? And that would. Now it's not a trivial algorithm. I mean, I'll leave you to the homework. But with n squared comparison, you can do this. So if k is the number of dimensions is large, you're never going to use this.
Wait, so that doesn't go away as an exponent for the logarithm? Or, well, logarithm being a constant?
What? This thing?
The exponent.
K, if k is constant, then it's good.
Oh, okay.
But if k is an arbitrary thing, so that's why I said if k is fixed,
Oh,
this is okay. And there have been some, so if k is not fixed, so suppose the number of dimension is also equal to the number of points. So you have n points in n dimension, which is very odd. But if you do have it, you have this algorithm, which runs in roughly n to the power of 1.5 plus omega over 2. Omega is the complexity of the exponent of the firstest known matrix multiplication algorithm. Anybody knows what the value of omega is currently?
2.2.
Yes. 2.34 something. So 2.34 divided by half plus 1.5, whatever that is. So if the number of dimension is exactly n. And there is a randomized algorithm. Now this is why you can argue about randomized algorithms, right? See how nice it is? It's just order n. And for some fixed k. But none of the algorithms works really for general k. And this is a special case because it only works for k is equal to n. So our plan was to come up with a deterministic algorithm, randomized algorithm for arbitrary partial orders that works for any k. And so our complexity result is this, is k, this is there, n to the power of 2 minus delta k. And so this cannot ever go beyond n squared. So this delta k is a fairly complex function. I don't think we'll see it today. But as you can see, since delta k is greater than 0, this is less than n squared. And as k increases, this delta k tends to 0, but never reaches 0. And the factor k accounts for the fact that if you are checking dominance between 2 points, since there are k components, for each dimensions individually you have to check, right? So they have to check k. And okay, so that's the good part of. The fun part of randomized algorithm is this. Randomized algorithms tend to be fairly simple. It's like 4 or 5 lines. Most randomized algorithms. But the analysis is fairly complex. So what is our randomized algorithm? Well, sort the points. So again, we have n points in a k-dimensional Euclidean space. And in our case, we are assuming, so first, in this model, we are assuming that the points are picked uniformly at random, like I defined. Later, we extend it to arbitrary input, so where we don't make any assumptions. So that's our input. So first, we have these endpoints, we sort them in descending order according to the L infinity norm. Can anybody tell me what's the L infinity norm? So you basically, for each point, you compute the max of all the components. So for a vector, the L infinity norm gives the value of the vector, which is basically the max. So LP, so if I have a vector V, right? So the LP norm and the L infinity norm, you replace P by infinity, which is basically just computing the maximum of all the components. Is the pth root of the sum of all the components. So computing this L infinity norm is easy. So for each point, you just find the maximum coordinate, and based on those maximum coordinates, you sort the points. So that is going to be our set T of sorted points. And we pick points iteratively, one at a time from T, and insert in an element into the layer it belongs to. And we end when T is empty. It seems trivial. Of course, I left this most important part, insert the element into the layer it belongs to. I left the question how, what layer, what is I'm doing. So in order to keep these layers, we create a data structure which we have named hierarchical search tree. Now before going into the hierarchical search tree data structure, what would be the complexity? So the first thing is this: if P precedes Q in T, then Q cannot dominate T because we have sorted this point based on the max coordinate value. Right? So in one of the max coordinate value of P is greater than the max coordinate value of Q, then Q cannot possibly dominate P. because at least in one dimension P dominates Q. So expected runtime is n times Ti plus Tn. So Ti is the expected time to insert, which I have defined where, how, and Tn is the time to compute T, which is to compute the sorted order. And computing the sorted order is kind of trivial because you just compute the max and just sort normally. So it's k n times n log n. Okay. No, hold on. It's kn plus n log n. Yeah. It should be n times k plus log n. Okay. So what is the hierarchical data structure? First of all, layers are themselves are totally ordered, right? Because you have set of h layers, and it's just as numbers, right? The fifth layer is going to be less than the fourth layer and is greater than the sixth layer. So they are totally ordered. So you can think of them keeping them in a binary tree, binary search tree. But each node doesn't contain an element, but contains an entire layer. So hence you can keep this binary search tree, which maintains in each node a layer. During insert, we traverse B by querying corresponding HST. So each node of this binary search tree, which contains layers, these layers are contained in those HST. So each node of B is an actual hierarchical search tree instead of an element. So we have like two levels of trees. And so what we do is you start with the root, and if you look at if the root, and you take the new element, right, which you want to process, and you compare, you make this query of whether the HST inside the root, is there a point which dominates this point? If it does, then that means I should look in the right direction. If it's not, then there is a possibility that it may belong here, but it may belong higher up also. So I kind of hold this position and then kind of look in the left. Okay, so HST is defined so recursively because it's a tree. So it could be a singleton node. Our root has a number of non-empty children nodes, each of which is a root of an HST. And so instead of a binary tree, the arity of the tree, the number of children is k, the number of dimensions. If node Q is in the jth subtree of node P, then in that dimension, P will dominate Q. So think of it this way. Well, let's look at an example. This is a three-dimensional case. So suppose this is the root, right, or any node, and each of these children are created based on these hub spaces. Hub spaces are basically, if you have you have a hyperplane and one side or the other is a hub space. So you have an entire space, you create a hyperplane and say this side, that's a hub space. So here I have three hub spaces corresponding to three directions, x, y, and z. And so what we mean here is this: if Q belongs here, then that means for this half space, P dominated Q. So now what happens is this: if another point comes in and we know that in that hub space Y, that point dominates P, then we know that Q can never dominate that point. So we don't have to check this subtree. So that's why we don't have to make all comparisons, trivial comparisons. So that's the idea of above. If you have a Q query point, and if turns out that, so if a new point comes and turns out P dominates that point, then we are done. We should look at a right subtree on that main tree B. If not, we have to decide which of the subtrees we want to look at in this HST. And that is based on the fact that in which of the components the query point is dominated by the current root So this is fairly simple. It's just about doing this search instead of a binary tree in a K tree. Okay. Okay, so this is the thing I'm probably going to skip, but I'll still kind of go through it a bit to give you a sense of, although coming up with randomized algorithms and the nature of randomized algorithms are quite straightforward, the analysis is quite complicated. So what we want to do is to bound the time it takes to insert an element into this big data structure B. Because that's the goal, right? We start with n points, we pick one at a time using that max ordering. And once all the points have been inserted into their correct layer, we are done. So that's the time Ti. It's the time to insert a point I. And that's basically the search time, which is basically to find which layer it belongs to, and then the add time, which is to add it. Obviously, the add cannot be more than the search time. Once you know, it's kind of trivial. So we look at the search time. So the way we do it is this. First, we compute the expected number of nodes at depth D of an HST. So remember, these points are coming from a random order. So the expectation of the number of nodes at depth D comes from that distribution. BMK is the number of nodes visiting during the above. So the thing we want to compute is BMK, because that's the number of queries a point will make while figuring out whether some point dominates it or not. But we do this by computing AMD because it's easier. Actually, I forgot why. Anyway. So the search would be then BMK times log H, because the overall tree is a binary search tree, right? So you do that binary search traversal, which has log of H, because it's on the number of nodes would be H, because that's the number of layers. So you have H nodes in this larger top tree B. So it takes log H, number of nodes, to find your place. So that's where the log H comes in. And BMK is basically the number of nodes visited. So in each node, which is HST, you have BMK number of nodes you visit times the number of nodes you visit in the overall tree, which is log H. Okay. So we can write BMK as a sum over the AMI, and so it is the probability that a node P already in some HST dominates a query point Q. And you can so this formulation comes from this max ordering. If we didn't, so you would have been curious, like why you chose the max ordering? Because of this. We get this probability based on the fact that the points were chosen from the max ordering. And we can come up with a recursive definition, recursive formula for AMD. So this is the number of nodes at depth D of these HST. And is anybody familiar with this type of recurrence relation? As I say here, this is very similar to the binomial coefficient recurrence. So everybody knows the binomial coefficients, right? So it's n choose r, right? Which you can write as
n factorial over
n minus 1 choose r plus n minus 1 choose r minus 1. So that's another way of computing a binomial coefficient. So it's basically saying how many ways I can choose r elements from n elements. Now note that this formula is slightly more complicated because now we have these k terms. This is the same as this structure, but now we have this k terms. It's kind of an weighted thing. So clearly, this doesn't have a closed form. this cannot also have a closed formula. But you can kind of bound it by noting that this function AMD has like a bell shape. So there is a maximum at some point and then decreases. And you can kind of determine where that maxima is and only compute the portion left to it, because these things would be insignificant on the right side. Again, that involves lots of algebra. And once you do that, you get this expression for B and K. Remember, the B and Ks were the sum of the A and Ks, because B and K is the number of nodes visited, and the A's are the number of nodes in a particular depth. So you have to sum it over all depths. And so you get this extremely hideous expression on this. But it's less than 1. And that's all it matters. So if we add this to this, we get this. So the total runtime is k n to the power 2 minus delta prime k.
Wait, so we're guaranteed that 1 over log k is greater than log base k of 1 plus 1 over k?
Yes. All this thing I was talking about was for random p. What if I have given arbitrary p? So what you can do, instead of having only one HST per node in B, you didn't miss any important part. You can have a list of HSTs, and each is size of square root of n at most. So instead of, and then what you do is this. So because P here is not random, you can't do this thing which we did earlier of computing the expectations and stuff like that. But because now you can keep this as a series of HST, what you can do, once a square root of n set of points arrive, you randomly permute and then create an HST from it. So you still kind of get to that randomness. That's why you, instead of having one HST, you can maintain a series of HST. And using that, you can, so this was this, right? So using that, you get a slightly weaker result. Now we have k squared instead of k. Then we have n to the power of 3 over 2 plus log k minus 1 over 2. So this is this is almost surely half, right? Slightly less than half. That's all we care. But obviously it will tend to 1 as k tends to 0. So you still get what we want, except that we have a k squared here instead of k. But remember, our original goal was this should be always subquadratic in k, and should never explode beyond n square. Now obviously, what are the open problems? The open problem is to come up with a deterministic algorithm which has this property that doesn't go beyond n square. As I said, trivially you can look at all points and compare each other and done, but that takes n square time. And as far as I know, it's still open. So if anybody wants to solve it, feel free.
I have a question. So why is it that you can't just do, so you're using this binary search tree, right? So why can't you, and as you pointed out, this is kind of like sorting in higher dimensions, right?
Mm-hmm.
So why is it that you can't just insert one element into your tree, just some random node, and then test, does this dominate, and then test on a new point, is this dominated by this point, or does it dominate that point? And if it is dominated totally, then it goes to the left. And then if it dominates and it goes to the right, if neither of those, then it just gets added to the layer in that point.
Yes, but the problem with that is you have to have deletion mechanisms.
Why?
Because there could be another point coming in which dominates one of the points.
Well, that's just a tree balancing thing.
The thing is, with high dimensional tree, you would not yes. So one way to kind of get a deterministic result, if you can find a balancing mechanism for HST.
Okay.
But in higher dimensions, it's hard to imagine how you're going to rotate trees because you have more than 2 children.
Why do you have to though? Because isn't the question, is this point dominated or not? Which
No,
is
no, the
binary.
problem is this. Once you keep adding points to this node, how you have to search the new points over all these points.
No, you just need one representative, don't you?
You can't, that's the point.
Why?
Because these are incomparable. So that's the main problem.
But I thought the point was that for any layer,
So for any layer,
It's
because
not-
these are non-dominating, right?
Right.
One cannot represent everyone.
why?
Think about it. Well, if it can, it will be done.
Okay.
So yeah, that's an open problem. Any other questions? I mean, you can ask questions. I like questions. Of course, there is a parallel problem called computing the convex layers. So you have a set of points. Where did I put the green? So you have a bunch of points. Oh, this is really bad.
Yeah.
I think I will not be able to reach that one.
Just throw the other marker up.
So you have a set of points. And the convex layer problem is that this is the first convex layer. This is the second convex layer, and this is the third convex layer. So that's a kind of parallel problem. It looks very similar, but convex layer and maximal layers are completely different because as you can see, if you're in a maximal layer,
What if you did polar coordinates?
what?
Would it be the same problem if you did polar coordinates?
Yeah. Well, actually, I don't know how you're going to do polar coordinates in higher dimensions.
That's a good point.
You can, but you need many angles, and it creates, for each dimension, so you'll have one r, that's the modulus of the vector, and you have as many thetas as for each dimension. So it's just a messy thing, don't even think about it. Well, you can't think about it, but anyway.
You, for comparing layers, but inside the layer, do you store them in any particular order, for example, dimension
No, that's where the
1?
HST comes in. We store using this hierarchical search tree. So we're doing this dimensional partition. Each children is a partition of one of the dimension. It's similar to the KD tree, if anybody has. So there's a very important problem in geometry, computational geometry, it's called nearest neighbor queries. So you have a set of points, so given another point, you want to find the point closest to it. It's an extremely important problem because machine learning and all that requires fact, because the points could be data. And KD tree is a partitioning of space into different dimensions. So unlike HST, which has k children corresponding to k dimensions, KD tree will still be binary, but it has a sequence of, so the first, suppose you have a 3-dimensional case. So you start at the root, first 2 children correspond to the x-axis, left and right. And then the second level, you would have y-axis. At the third level, you have z. And then you again repeat to x. So instead of having 3 children, you have 3 layers to create it. And unfortunately, if you do that kind of data structure, you get that log n to the power of k terms. And if the k is fixed, that's great. But if k is arbitrary, then you can't do it. But yeah, that's another thing to come up with a better solution for nearest neighbor problems is still very active. That's why the diameter thing we were trying to do with Max, it's a similar problem here. given a set of points, right, like that, you want to find 2 points which is furthest apart.
Yeah, but did you say
So
that?
for us, it's an online problem. So that's the computing the diameter of overall set. For us, you are given a set of points, but the queries are rectangular regions, or in high dimensional hyperrectangles. And you want to find the diameter of the 2 points furthest apart within the rectangle.
I thought you said that the nearest neighbor query was very different from the diameter problem.
In the overall scheme of things, when I'm explaining to them, they are very similar.
Oh.
In the context of nearest, whether the nearest neighbor queries are, well, yes and no. In certain respect, if the points are on a Hamming space instead of a Euclidean space, do you know what a Hamming space is? It's instead of computing the differences in the coordinate and doing this square root thing, it's basically 0, 1, and you just want to figure out the difference in the number of bits. So think of the points are in a hypercube, and each is represented by a 0, 1 vector, and the distance between 2 points is the number of mismatched bits. So Hamming.
Okay.
In that setting, the nearest neighbor query and the furthest point query is dual of each other,
Oh, okay.
but not in Euclidean space. It's yes and no. He does ask a lot of questions.
It's true.
That's better than asking no questions.
Thank you.